Welcome to Math Explore Infinity, your passport to navigating the world of mathematics as smoothly as a polynomial function. As the great Wayne Dyer once said, you have two choices, be miserable or motivate yourself. By subscribing to this channel, you are not just choosing to explore, grow, and get motivated, you are also becoming a part of our vibrant community, a community filled with inquisitive minds eager to dive headfirst into the infinite universe of mathematics. But consider the flip side as well, right? I mean, if you choose not to subscribe and prefer to admire the beauty of mathematics from a distance, you might actually miss out on some mind-bending insight, right? Horizon expanding exploration, and also those eureka moments that can reshape your perspective forever. So please don't let, don't settle for being a mere spectator in this mathematical symphony, right? I mean, don't let I would say the fear of missing out get the best of you. Instead, choose motivation over misery, definitely, by subscribing now and be at the forefront of this mathematical enlightenment revolution. So today we are going to explore a mathematical concept, right? That is as beautiful and powerful, notably Hilbert spaces. Well, you might wonder why you should be excited about this abstract sounding topic. So to help you understand the significance of Hilbert spaces, let me paint a picture for you. So imagine for a second, right, that you own a hotel with an infinite number of rooms, right? I mean, each room numbered with a positive integer, right? I mean, room 1, room 2, and so on. So, well, here is where it gets kind of interesting. Suppose, assume that you have an infinite number of guests arriving, and each guest needs a room. Intuitively, it might seem impossible to accommodate everyone, right? I mean, after all, you cannot count to infinity, definitely. So, here is where Hilbert spaces come to the rescue somehow. I mean, they provide us with the mathematical tools to understand and actually work with these infinite scenarios. I mean, it's like having a magical room allocation, right? Magical room allocation system that ensures that every guest, no matter how many, gets a room without anyone having to leave. So this infinite hotel analogy shows the power and elegance of Hilbert spaces in handling infinite dimensional problems. So again, I mean, why this matters, right, beyond a hotel analogy? Well, in the real world, we often deal with continuous data, right, functions and infinite dimensional spaces. For instance, in quantum mechanics, particles can exist in an infinite number of states, and Hilbert spaces actually help us make sense of that. Also, in signal processing, Hilbert spaces are really helpful in analyzing and manipulating continuous signals somehow. So, to cut it short, right, studying Hilbert spaces is not just about abstract mathematics, it's about also unlocking the door to a wealth of applications and deepening our understanding of the mathematical structures that underpin our world. So, as we embark on this journey through Hilbert spaces, please remember that you are not just learning mathematics, you are also equipping yourself with a powerful toolkit for exploring the intricacies of our universe. So, we start by defining some basic concept that we will need. So, definition. So, let H, right, capital H be a vector space. So a scalar product, let's put it in color, a scalar product so let's denote it by those brackets, right, is a bilinear form on h cross h, right, with values, with values in R, right, such that let's use bullet points, such that it is symmetric. So the scalar product of u and v is the same as the scalar product of v and u, like this holds for every uv in H, right? So this is the symmetry property. Just put it in color, symmetry. Right, so you also have the bilinear form should also be positive. So scalar product of u and u should be greater or equal than 0, right, for every u in H. Right, so this is positive. And finally, it should be definite, right? So scalar product of u and u should be different from 0 whenever u is actually different from 0, right? This is the 0 of the Hilbert space. So this property says it is definite. Right, so well, so let me just put it probably. So this property, is often resumed by saying that this is, positive definite. Scalar product should be positive definite, right? So, and you can write it this way. This means the scalar product of u and u should be strictly greater than 0. For every u belonging to, let me just drag it a bit to the left. Good. For every u belonging to H, right? To H, but u different from 0. Of course, the scalar product actually satisfies the Cauchy-Schwarz inequality. So scalar product satisfies the Cauchy-Schwarz inequality, right? And this, the absolute value of the scalar product of u and v is less or equal than the scalar product of u and u to the power 1 over 2 times scalar product of v and v to the power 1 over 2. The square root, right? For every u and v in H, right? You can actually prove this, right? Prove the Cauchy-Schwarz inequality in your spare time, right? And if you face any issue, or you're of course welcome to drop your question in the comment. So it follows from, so let me just write it. It follows. It follows from the Cauchy-Schwarz inequality that we just abbreviate by CS. So it follows from the Cauchy-Schwarz inequality that the quantity defined by this, right, norm of u equals to the square root of the scalar product of u and u, right? So this defines a norm right? This you can easily check, right? So before writing down the next definition, so let's recall a famous property. Let's recall the parallelogram identity. Parallelogram identity. So we call it so let's call it 1, because I think we will refer to it later on. So it says that the norm of A plus B over 2 squared, right, plus the norm of A minus B over 2 squared, right? This is equal to 1 over 2 times the norm of A squared, right? Let me just write it down here, plus the norm of B squared. Of course, this holds for every A and B in H, right, in the vector space H. I've been talking about Hilbert spaces, but we haven't defined Hilbert space yet. So now let's define what a Hilbert space is. So definition. A Hilbert space write it here. A Hilbert space H, right, is a vector space. It's a vector space equipped or endo with a scalar product. Right, such that H is complete, right, for the norm arising from, let me just write it, for the norm arising from the scalar product. The norm we defined above or previously. From the scalar product, right? So this means, this norm, right? Norm defined by the square root of this scalar product. Okay, so in what follows, right, H will always denote a Hilbert space. So let's have an example of a Hilbert space. For example, you can actually think of the space L2 that we discussed. So L2 of omega, right, equipped with the scalar product let's define the scalar product. Scalar product of u and v is equal to the integral over omega, right, of u of x, v of x, d mu x, right? So this L2 of omega and though with this scalar product is a Hilbert space. Right, and of course, in particular, small L2 is a Hilbert space, right? If you take omega to be, just write it in particular. small L2, right, is a Hilbert space as well, right? I mean, you just need to, to put omega to be n, right? And of course, mu, the measure should be now the counting measure, right? Mu is the counting measure. And of course, the scalar product will be something like, take two elements of the space, small L2, so the scalar product should be defined as the summation over the n of un times vn. Okay, now I think we know what the Hilbert space is, so we can have our first proposition, proposition 5.1. Good, so every Hilbert space, right, is uniformly convex. Every Hilbert space H is uniformly convex. And that's reflexive, right? This is just a consequence of the Millman-Pettis theorem. So I strongly invite you, if you don't know what uniform convex space is, strongly invite you to watch my video on uniformly convex spaces and also the Millman-Pettis theorem, which was actually a very striking theorem, right? That, a geometric property actually implies a topological properties, right? Uniform convexity implies reflexivity, which is really amazing. So every Hilbert space H is uniformly convex and thus reflexive. Right, this is by Millman-Pettis. Let me just highlight that. I think I will put the link to the video, to the corresponding video at the upper right corner here. So let's go into the proof, right, which is rather straightforward. So proof, let epsilon. Again, for your recall, uniform convexity means that, if you actually slide the whole of length epsilon, right, in the closed unit ball, right, then its midpoints should be contained into the ball, right, of radius 1 minus delta, right, for some delta that we have to find. So let epsilon positive and u and v in H, right, satisfy the norm of u. This is the norm arising from the scalar product because H is a Hilbert space. Norm of u is less or equal than 1 and norm of v is less or equal than 1. So u and v actually contain the closed unit ball, and the norm of u minus v is slightly greater than epsilon. So again, as I said already, we want, in order to prove uniform convexity of the space, we want to show, we want to show that there exists a delta positive, right, such that the norm of u plus v over 2, right, is actually slightly less than 1 minus delta. So this is what we want to do. So in view of, this is just, consequence of the parallelogram identity. So in view of the parallelogram identity, right? We have the norm of u plus v over 2 squared, right, is strictly less than 1 over 2 of the norm of u squared plus the norm of v squared. Of course, this minus the norm of u minus v over 2 squared, right? But remember, this u and v are contained in the closed unit ball, so the norm are less or equal than 1, and also we were given the norm of u minus v to be strictly greater than epsilon, so this quantity here is actually is strictly greater than epsilon over 2 everything squared. So this is strictly less than 1 minus, we just write epsilon over 4, epsilon squared over 4, right? So this means the norm of u plus v over 2 squared is strictly less than 1 minus delta, right? With delta being equal to 1 minus, let me just write it properly, 1 minus epsilon squared over 4, right, to the power 1 over 2. And this, of course, is strictly greater than 0. So this means H is uniformly convex, so we are done, because as I said earlier, reflexivity is just a consequence of the Millman-Pettis theorem. Okay, so now let's state our first theorem, I think the main theorem of this lecture, which is a very important theorem, right? Because it is really applicable in various domains such as stochastics and I mean optimal control and so on. So this is projection onto a closed convex. Let me just write it. Projection onto a closed convex set. Okay, good. So let's call it K, right? B a non-empty closed and convex set. The name just highlight. I mean, non-empty is important, closed and convexity, all of them are important, right? Then I mean, for every f in H, right, there exists a unique u in K, right, such that and let's call it 2, relation 2, such that the norm of f minus u, or u minus f, it's actually the same, is equal to the mean of the norm of f minus v, right? I mean, the mean is attained, I mean, it should be the inf, right, but I replace it by the mean, because it is actually attained, which is just the distance of f to k. So moreover, u, we put it in quotation. So moreover, u is characterized, I mean, we can even characterize the arg mean. U is characterized by the property and we call it 3, right? U is in K, of course, right? And the scalar product of F minus U, V minus U, right, is less or equal than 0. And this should hold for every V in K. Right, so U is actually, U is the projection of F onto the space K, right? And it is denoted by, I think we often write, or we will write, right, throughout this lecture, PKF, right? Okay, so property 3, right? Let me just write it. Inequality 3 says that the scalar product, says that the scalar product of the vector, this is an abuse of notation somehow, of the vector UF, right? With any vector say UV, right? When V in K, of course, right? That the scalar product is less or equal than 0. Let me just write like this, right? Well, this means that this means the angle, say theta, right? So that the angle, let's call it theta, right? Determined by those two vectors, is greater or equal than pi over 2, right? So so just for you to, let me just try to sketch it. So say you have, this would be, for instance, this would be, for instance, the convex set K. This is obviously convex, right? And say you have a point, say F somewhere here, right? So let's assume that the projection actually leads to, say, yes, to something like this, right? And let me just mark this place to be, let's say this is U, right? This is projection of F onto the closed and convex set K. Well, say you have another good, say we pick a vector V here like this, right? So this angle theta, right, should be actually, it's obviously greater than pi over 2. Okay, so so let's go into the proof, right? So proof. Okay, let F in H, right? So we start first by showing the existence, right? So existence. Usually people show uniqueness, right? And then, but let's start with existence actually. So there are actually two approaches to prove existence, right? So let me just go with the, with a rather direct argument, right? So, well, I'm thinking, so which one should I do? Let me just go with the direct argument, right? So I think the direct argument would be, so you don't have to go and watch some of my previous video. So okay, so So this is a direct argument, right? So put G to be the inf, right, of norm of f minus v, right? This is v in k. So we know that this is by characterization of the infimum. So this means that for every v in k, right, the norm of f minus v, g is less or equal than norm of f minus v, right? And also for every epsilon positive, right, I can find v of epsilon, right, in k, such that if I add something to the, to the infimum, it's no more the infimum, right? So the norm of f minus say no, the epsilon first, not jump steps, so that this is strictly less than d plus epsilon. So this is just the characterization of the infimum, right? Now, since look at this second part here. Good. So look at this second part here. This holds for every epsilon, right? So this means for every n, right, I can basically construct a sequence. So there exists a Vn, right, in K, such that of course T is strictly less than norm of F minus Vn, right, which is less than D plus no more epsilon, but say 1 over n, right? N greater or equal than 1, of course. So you see that from this, we have that the norm of Fn minus Vn actually converges to D. So such a sequence, Vn is called minimizing sequence. Those familiar with calculus of variation, they really know this, right, by heart. So such a sequence, Vn, is called minimizing sequence. So, well, this was just to motivate, right? Because I'm going to use it. So let Vn, right, be a minimizing sequence, right? A minimizing sequence for, we call it 2, right? So this means, let me just write it again. So Vn is a sequence of element of k, right? And just call it Gn, which is defined to be the norm of f minus Vn, so that this actually converges to G. So our claim is that Vn is a Cauchy sequence. So claim Vn is a Cauchy sequence. Right? The proof is rather, it's not difficult. Indeed, this follows from, again, the parallelogram identity. Right? So applied with, say, A equals F minus Vn, just, right? And B equals F minus Vm, right? So you will get something like, if you apply the parallelogram identity, so you get norm of F minus Vn plus Vm over 2, right? This squared, right, plus the norm of Vn plus Vm, oops, over 2 squared. So this is less or equal to 1 over 2. This will be dn squared plus dm squared, right? But observe that because k is convex, right? So we know that this quantity here, I mean Vn plus Vm over 2, right, is still an element of k because k is convex. And by definition, so this means that that the norm of f minus Vn plus Vm over 2, right, is actually greater or equal than g. This is just by definition of the infimum, right? So it follows that. So if you pull that, I mean, if you pull this quantity on this side, so you get that the norm of Vn minus Vm over 2. Let me just check something. I think I did a mistake here. This is minus, not okay. Good. You get that this squared, right, is actually so let me just remove the squared, right, and go a bit faster. You get that this is less or equal than maybe I should keep this squared back, right? So to avoid working with square root. So this is less or equal than 1 over 2 plus g squared, right, minus g squared, right? But this quantity here actually, let me just use another color. So this quantity here actually goes to 0 as n and m goes to plus infinity, right? So this means the norm of Vn minus Vm, right, goes to 0 as m and n goes to plus infinity. So Vn is obviously a Cauchy sequence. Good. Therefore, the sequence Vn converges to some limit u in k, right? Because k is closed, right? And I mean, closed subset of a complete metric space is complete. So therefore, the sequence just write it, Vn converges to some u, right, into k, right? Because as I said, k is closed, right, and h is complete. So Vn converges to some u in k, right, and the norm of f minus u, right, is equal to g, right, which is the infimum of the norm of f minus v over the v in k. So this proves existence. So in second step, we are going to prove that the equivalence of 2 and 3, right, that I mean u is even characterized by the scalar product of the vector uf and any vector uv, v in k is actually less or equal than 0. So in B, we prove equivalence. Let me just write, in B we prove that 2 is equivalent to 3. This is what we do. Okay, so let me just recall again what we want to show. So we want to show that, I mean, this was 2. 2 was that the norm of f minus u is equal to the mean the norm of f minus v, right? What the v in k? And show that this is equivalent to 3, right? 3 was the fact that u is in k, right? This is obvious already. And the scalar product of f minus u and v minus u, right, is less or equal than 0 for every v in k. Good. So we start with first implication. So let me just put it. So assume u is in k, right, and satisfies two, right? So and let we call it w now in k, right? So we have by convexity, of k that the vector v that I define to be 1 minus t u, right, plus t w for every t in 0, 1. You have that this v is in k, right? And thus, by definition, norm of f minus u is actually the inf, so this is less or equal than the norm of f minus v, right? But let me just kind of not really recall, but draw your attention at the fact that this is again the norm of f minus u. Just replace v by its value, so minus t u minus w. So good. So therefore, if you square every side of the inequality, you get that the norm of f minus u squared, right, is less or equal than the norm of f minus u squared plus, minus 2 times t, right, f minus u, scalar product of f minus u and w minus u, plus t squared of the norm of w minus u squared, right? So this means, because now here you can actually cancel this and this, right? So this means 2 times what we write it here, 2 times the scalar product of f minus u and w minus u is less or equal than t. You can also cancel t, right, because t is positive, so this is less or equal than t times the norm of w minus u squared, right? And this, of course, this holds for every t in 0, 1. So if you choose, make t goes to 0, if you make t arbitrarily small, right, small enough, we get 3, of course. We get 3. And maybe this 3 can fit here. Good. Right, so this means that the scalar product of f minus u, w minus u, height is less or equal than 0 for every w in k. Okay, good. So let's take the reverse implication. So conversely, assume that 3 holds, right? Assume that u satisfies 3. Just highlight 3, right? So just for you to know that, to remember that 3 was actually a property. Then we have the norm of u minus f, right, squared, right, minus the norm of v minus f squared, right? This is equal to 2 times scalar product of f minus u and v minus u, right? Minus the norm of u minus v squared, right? I mean, this is, you can actually check this right easily. There's no black magic here. But by assumption, right, this is actually less or equal than 0, right, for every v in k. So this is less or equal than 0 for every v in k, right? So this means that the norm of u minus f, right, or you can reverse it even if you want, norm of f minus u is less or equal. I mean, you can also kind of square root both sides of the inequality, so you get the norm of f minus u is less or equal than the norm of f minus v, of course, for every v in k, right? So this means because u is in k, right, so this means that the norm of f minus u is the mean, right, of the norm of f minus v, because u is an element of k, so this is equal to the mean of v in k. So good. Once two. Good. Now finally, we show uniqueness, right, which is rather straightforward. I mean, since that we even prove the uniqueness. So assume that u1 and u2 satisfies. I mean, you assume that u1 and u2, right, satisfy we call it 3, yeah. So this means, let me just write it, let's put it 4 and 5. So this means the scalar product of f minus u1, and then we still use v minus u1, right? It's less or equal than 0 for every v in k, and also the scalar product of f minus u2, v minus u2, is less or equal than 0 for every v in k, right? So you should choose v. So choose v to be u2, right, in 4, right, and v to be u1. Oops. In 5, let me just highlight this. In 5, right, we get so we should make that those choices. So we get that just go slowly. Scalar product of f minus u1 and u2 minus u1 is less or equal than 0. Scalar product of f minus u2, u1 minus u2 is less or equal than 0. So you get this, right? But observe that, I mean, here you can even change the, I mean, can even write it as u2 minus f, right, comma, oops, comma u2 minus u1. Of course, this less or equal than 0. So if you add the above inequalities together, you get that. So adding the above inequalities together, so maybe we get, if you add both, then you get that the norm of u2 minus u1 squared, right, is less or equal than 0, right, and consequently u1 and U2 coincide once uniqueness. So with this, we end the proof of the projection theorem, right? As I said, this is actually a very important theorem, as it really plays a vital role in many applications and also other field of mathematics, like in stochastic. If you want to prove, for instance, in stochastic, if you want to prove that the conditional expectation actually exists, then you need to rely on the projection onto a close subset. Yeah. And also, yeah, if you want to prove also the tower property, right? The tower properties actually says that, to keep it simple, it says yesterday prediction, right? Yesterday prediction of today's prediction of tomorrow is equal to yesterday prediction of tomorrow. So to prove that, it's like you use projection, right? So you should project first on, so let me just draw it, right? So to make things clear, say you have this, say, let me duplicate this. Say you have this is K1, right? Here you have K2, and then you have a point, say, let's call it F, right? So you should project first on this space, right? So you get here U1, and then you project back on this space, say U2, right? So this U2 is actually the same as projecting F directly on K2. So this is basically the idea of the tower property also as well. But anyway, we are not into stochastic, so let's keep going with our lecture on Hilbert spaces. So remark. So let's have a remark first. The above theorems. Oops. So the above theorem holds true, right? If K, right? If K is non-empty, closed, and convex. Closed and convex subset of a uniformly convex Banach space, right? So you don't necessarily need a Hilbert space. So let me just highlight uniformly convex Banach spaces. Holds true. Okay, so proposition. So let's have a proposition very quickly about projection. Proposition, I think it is 5.3, if I'm not wrong. Let K be a subset, right? Be a non-empty, of course, closed convex set. Then the projection onto K projection onto K that we call okay, does not increase distance. Say that the projection is non-expansive. Let me just write it. P case is non-expansive. Okay, well, so this means that the norm of the projection of f1 onto k, right, minus the projection of say f2 onto k, right, this is less or equal than the norm of f1 minus f2, right? Of course, this is for every f1, f2 in H. Okay, good. So let's go into the proof very quickly. So let, of course, let f1, f2 in H, right, and put u1 to be the projection onto k of f1 and u2 to be the projection onto k of f2, right? Then we know how, then by characterization of projection, right? Then by characterization of u1 and u2, right? We have, let's call it 6 and 7. We have that, this is what we saw in the previous theorem. So the scalar product of f1 minus u1 and v minus u1, right? This is less or equal than 0 for every v in k, and then we also have the same thing, f2 minus u2, v minus u2, less or equal than 0 for every v in k. And again, we do the same trick, right? So choosing v to be u2 in 6, right? And v to be u1 in 7. Right? And adding the corresponding inequalities together, and adding the corresponding inequalities together, right? We obtain, or we get that this scalar product of f1 plus f2, right, plus u2 minus u1 and u2 minus u1, right? This is less or equal than 0, right? Now you use the linearity of the scalar product to get that the norm of u2 minus u1 squared, right, is actually less or equal than the scalar product of f1 minus f2, and this should be minus, yeah, and u2 minus u1, right? But this is less or equal, this is just the consequence of Cauchy-Schwarz, and the norm of this times the norm of u2 minus u1, and this is by Cauchy-Schwarz. Now if you simplify, then you get that the norm of u2 minus u1 is less or equal than the norm of f2 minus f1, right? And this is what we had to show. Okay, good. So now probably the last corollary. Let's have a corollary. The last corollary of this lecture, because I think yeah, we are going a bit more than 1 hour. Okay, so corollary 5.4. Yeah. So assume that M as a subset of the Hilbert space H, right, is a closed linear subspace, right? Now let F be an element of the Hilbert space H, right? Then the projection of F onto the sorry, not K but M, the projection of F onto the closed linear subspace M is characterized by we call it 8, right? This is characterized by U is in M, right? And the scalar product of F minus U, V is equal to 0 for every V in M. So we no more have an inequality, right? But an equality here for the case where M is a closed linear subspace. So moreover, PM, right? This is a linear operator, and the projection onto the closed linear subspace is a linear operator, right? That we call the orthogonal projection. Good. So let's have a look at the proof very quickly. Good. So so the good thing is that by 3, right? We proved this already. So by 3, we have we know that projections are characterized by scalar product of F minus U and V minus U, right? This should be less or equal than 0 for every V in M, right? And this we know already. But because M is a linear subspace, right? We even have scalar product of F minus U, TV minus U, right? It's less or equal than 0 for every V in M, right? This also holds, right? Because M is a linear subspace, and for everything in R, right? So it follows. So from this we can conclude, it follows that 8 holds. So it follows that 8 holds. Why? Let me just let me put it in color, because from this, right? So what you can do is that you can say that, okay, for T strictly positive, right? What do we get is that F minus U or V, right? This scalar product is less or equal than 1 over T, right? And of, we put it in bracket, scalar product of F minus U comma U, right? But this actually goes to 0 as T goes to plus infinity. So you get that the scalar product of F minus U comma V is less or equal than 0. But on the other hand, for T strictly less than 0, right? The inequality changes, right? We rather get this minus V is greater or equal than 0 for every in M. So therefore the scalar product should be 0. Okay, so 8 holds, right? Now conversely, if U satisfies 8, right? So if 8 holds, we have scalar product of f minus u, v minus u, right? This will be equal to 0 for every v in M, right? Because, I mean, saying that 8 holds means that scalar product of f minus u comma v is equal to 0 for every v in M, right? But u is actually in M, so this also holds with u being replaced by v, and therefore the difference is 0. So, okay, so this holds, so, and this means u is exactly the projection of f onto M. Good. So I think we are done, because I'm just going to write that. I mean, you only have to prove linearity of PM is obvious, right? I mean, you can actually check it maybe yourself, yeah. But I mean, it's not. Well, let me just do it for you. So I mean, let's say f1, f2 in H, sorry, right? And then you take an alpha in R. Now put u1, right, to be the projection onto M of f1, and u2 to be projection onto M of f2, right? Then I mean, we know by characterization of projection, we have f1 minus u1 comma v. This is equal to 0 for every v in M, and then we also have the same thing for u2, right? With f2 minus u2 comma v equals to 0, but I can even multiply it by alpha, so I can write directly alpha f2 minus alpha u2 comma v. This scalar product is 0 also for every v in M, right? So this means if you add everything up, you get that the scalar product of f1 plus alpha f2, right, minus u1 plus alpha u2 comma v, this is 0 for every v in M. But this means, I mean, this is exactly the characterization of the orthogonal projection of f1 plus alpha f2 onto M. So this means u1 plus alpha u2 is exactly the projection onto M of f1 plus alpha f2, and this actually shows linearity, right? Because remember, u1 is just the projection onto M of f1, and u2 the projection onto M of f2. So with this, we conclude this lecture and this video as well. Thank you for watching the video, and see you again in the next video.